So this is lab 4, which is circuits. To introduce the purpose of the lab, this lab will use the principles of energy and current conservation in order to study the behavior of ohmic resistors and capacitors, usage of multimeters, and how to predict circuits with resistors in series and parallel, how they will behave. So the fundamental principles include energy conservation, or the loop rule, the node rule, current conservation, or charge conservation in steady state, time dependence in RC circuits, and Ohm's law. So the main physics ideas include voltages and currents are constant in a steady state circuit. A series circuit has a current that flows through all resistors the same amount. A parallel circuit has voltage the same across all resistors, but the current flowing through each is different. And then I have loop rule and charge conservation pictured separately. So results overview, the values gathered for current and voltage were similar to those predicted. For RC circuits, the magnitude of the current is indeed time dependent. So here are some photos of the circuit as required by the rubric. In the middle, you can see the one with the light bulb, and the light bulb is actually glowing. So for the experiment, we are assuming wire resistance is negligible and ammeter resistance is negligible. The circuit is the system, the room is the surroundings. The initial conditions was a simple series circuit in parallel using batteries, resistors, and ammeters. So the series circuits, details, and data, we first considered a simple series circuit. We had to simulate this due to limited supply, as there are 2 ammeters included in this one. The prediction was that the current was 0.0204 amps, and this was done with Node's law, where the current at 1 and the current at 2 was equal. RE equivalent was calculated as seen there, and then the current was calculated using delta V over R. The actual reading was 0.02 amps. This reading was negative 0.02 amps when reversed, so the predictions were roughly correct. One of the ammeters was then replaced with a voltmeter. The new voltage difference was read as around 3 volts, whereas the current was around 0 amps. This is due to the fact that this is now an open circuit, meaning there is no current. In an open circuit, the potential difference must be equal to the power source, which adds up to 3 volts. So we then closed the circuit with a wire and used the voltmeter to measure the potential difference for each part by touching the 2 leads to the 2 points needing to be measured. There is our data collected there, and for the loop rule, the sum should be 0, and our actual sum was 0.41 volts. Which has to do with user error that will be discussed later. Details, so the charge is still equal to 0.2 amps. This reading doesn't change because the voltmeter has really high resistance, meaning no current is flowing through, so the current path should stay unchanged. Once connected with the 100 ohm resistor, 0.05 amps was read. The resistance of this part must decrease as less current is coming into contact with the resistor. So here is the graph completed. C to D has a downward slope, D to E is constant, and then E to F has a downward slope all the way down to 0 volts, where it is then constant, all the way through H. So here's the actual experimental calculation for the 470 ohms, 1000 ohms, the wire, and the ammeter, just using the voltage divided by the current in order to get the resistance. So our final answers are 49.5, 120, 0, and 0 ohms. So the RC circuit, details, and data. The batteries were then connected to the 10 ohm bulb and capacitor in series. The light of the bulb was bright and then started to dim until it went out. The capacitor is then directly connected to the bulb. Again, it lights up and then dims until it's out. When charging and discharging, the current is decreasing from its maximum value to 0. The resistance of this part must decrease as less current is coming into contact with the resistor. It took 15.4 seconds to charge the capacitor and 18.74 seconds to discharge with the 10 ohm bulb. For the 20, it was 26.2 to charge and 43 to discharge. So for the RC circuit, time dependence voltage, the creation of a circuit with a 9 volt battery, a 200 capacitor, and a 30 ohm light bulb. We measured the voltage across the capacitor with the voltmeter. Here's an example of the circuit, and then up there are the equations we'll be using to linearize the data. So here is our data for a time of 0 to 20 seconds, and then the delta V was calculated, and then we got the natural log of the delta V divided by the delta V initial, which in this case was 9, and then we were able to plot this line. It is linear with a slope of negative 0.166 and a y-intercept of negative 0.0088. Because negative 1 over RC is equal to the slope, we can actually calculate the time as seen here. We got 1 over 0.166, because the negatives cancel out, is 6.02 seconds. And the expected would have been 30 ohms times 0.2, aka 6 seconds. So these are very similar values. A model would have been an ideal circuit for the similarity and differences section of our discussion. In real life, resistances are provided by the ammeter and other aspects of the circuits that we have created. So possible sources of error, we didn't include the resistance of the ammeter, and also the orientation when measuring the voltage difference at different places may not have been accurate, meaning the way we were holding the actual measuring devices. So what if we were doing this lab in real life and used an actual ammeter? So this is essentially just asking the difference between real life and virtual, since we did do it in real life. Basically, in real life, an ammeter would provide resistance, meaning the charge values are less than they would be for a model. If we used a real battery to charge a real capacitor with no resistor, it would have immediately gone to full charge, but in real life, the wires do provide resistance, meaning it's going to take longer to get to full charge. Thank you for watching. The conclusions include the formula used to predict these values are similar/accurate to the actual experiment being ran. Thanks so much.